In 10.1b, we're going to look at significance tests for a difference in proportion. All right, so what are the conditions for constructing or conducting a two-sample z-test for the difference in proportions? Well, the good news is they're the same conditions we used when we did the intervals, the confidence intervals for P1 minus P2. Nothing's changed there. That's good news. Now, to get a more precise estimate of the standard deviation of the sample statistic by combining, we call that this pooled sample proportion. And we use the estimates given by the two independent samples. This is unique to doing a hypothesis test. This is not something you do when you do a confidence interval. It's only when you're doing a hypothesis test with a null and alternative hypothesis. So what does this mean? It means this. We assume that the null is true, right? We assume that P1 is equal to P2. That's the assumption we make when we do these tests. And because of that, we can combine the sample proportions for a more precise estimate of the true p-value. So calculation-wise, here's what we do. We take the number of individuals with the outcome for sample 1, add it to those of sample 2, and then we combine the sample sizes. This gives us the pooled proportion, and this pooled proportion is the value that we use when we check large counts and when we find the standard error of the difference. And I'll show you this in a little bit. All right, so let me just model this. Okay, example here. Researchers designed a study to compare the proportion of children who come to school without eating breakfast in 2 low-income elementary schools. A simple random sample of 80 students from school 1 found that 19 had not eaten breakfast. At school 2, a simple random sample of 150 included 26 who had not eaten breakfast. More than 1,500 students attend each school. Okay. So how would I find my pooled p-value for this? Well, I'm looking for the outcome of those who did not eat breakfast, right? So I look at my table, and that's these numbers here. For school 1, there were 19 out of 80 sample that did not eat breakfast. School 2 had 26 out of 150. So it's the desired outcome divided by the totals, right? So when I do my pooled proportion, I'm just plugging those numbers in. 19 plus 26 gives me 45. 80 plus 150 gives me 230. And that gives me a proportion of 0.196. This is the value I'm going to use, again, in the standard error and to check large counts. Okay, so let me show you. When we do the standard error part, the denominator of our z-score, we're going to use the pooled proportion in that radical. Okay, notice we take that over N1, take that over N2. All of that, honestly, the calculator will do it for you. But just for reference, that's what's happening. It's taking a pooled proportion. And then we'll also use that when we do large counts. So what's the test statistic for a two-sample z-test? Well, it's exactly what we've done before. We take that standard error formula we just discussed and divide the difference by that standard error. And that gives us the z-score. Now, what is the 0? Well, the 0 is from the null hypothesis, right? It's usually the statistic minus the parameter, where your null hypothesis is going to be 0 because we're saying there is no difference between the two. Unless otherwise stated, it's always 0, and in this course it will always be 0. So don't worry about it being something else. Now, just keep in mind, when you're doing a z-test on two proportions, it still could be left-tailed, it could be right-tailed, or it could be two-tailed, right? So either way, same 3 kind of tests we've had before, it can happen with two proportions. Okay, so let's walk through a problem for the 4 steps. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 88 to 94, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005-2006, 19.5% showed hearing loss. And this data is reported by Arizona Daily Star in 2010. Now, do these data give convincing evidence that the proportion of all teens with hearing loss has increased? All right, so that's a clue that we're doing a significance test, and we're doing a 4-step process. So let's do the state step. All right, we want to test, and then we define our hypotheses, that the difference of the two proportions is equal to 0, that's my null, versus the difference of the two proportion is greater than 0. Why did I pick greater than? Well, we think that it's getting worse, right? 2005, 2006 is higher than then, the 88-94 group. we think it's getting worse. So we think when we subtract the newer sample from the older, it should be higher, right? So that's where we get the greater than 0. And I put the significance level at alpha equals 0.05 level, okay? Where P1 is the proportion of all the teens with hearing loss from 2005 to 2006. And P2 is the same thing, but from 1988 to 1994. And it's fine to put those ditto marks, that's okay. Just differentiate it at the end. Now, before we jump into the plan step, let's look at our numbers up here. What is P1? We're saying P1 is from 2005. Okay, so in my P1, I've defined it. My P hat value is 19.5%, so 0.195, and my sample size was 1,800. Then P2 was the 88-94 group. They had 15% of hearing loss and a sample size of 3,000. I need that information to move on to the plan step. Okay, on the plan step, I'm going to name the test. I'm going to perform a 2-proportion Z-test if the conditions are met. So let's run through them. 2 independent random samples were taken. Does that tell us that? Yes, 3,000 randomly selected teenagers. A similar study, we assume it's randomly selected. So yes, 2 different studies, different sets of years. It's random. Good enough. Now, 10% rule. More than 10 times 1,800 is 18,000. Were there more than 18,000 teens in 2005 to 2006? Yes. And is there more than 30,000 teens in 88 to 94? For sure. That's reasonable, so we just proved that it's reasonable. We'll move on. Now, for large counts, we have to stop. We have to use the pooled proportion here. So we have to do a little bit of work. So I created a table. All right. I am really concerned about the hearing loss people, right? So that means in my 88 to 94 group, there were 3,000. 15% of them had hearing loss. So if I multiply those out, round it to a whole number, I get 450 people. If I subtract that from 3,000, that gives me 2,550 who did not have hearing loss. Then I repeat the process for the 2005-2006 group, right? 1,800 sample size, 0.195 lost hearing. That means 351 people. Again, rounded to a whole number. Subtract that number from the 1,800, I get 1,499 who did not have hearing loss. All right, this gives me the information I need for my pooled proportion because I need the desired outcomes, the 450, the 351, and then the total of them to help me make my pooled proportion. So here's what I do. I take that 450 plus 351, that gives me 801. And then I add up the sample sizes, 3,000 to 1,800 gives me a total sample size of 4,800. That gives me a pooled p-hat of 0.167. This is what I use in my large counts. I do have to check it with both sample sizes, but that's okay. So, first sample size was 1,000 or 3,000, and I round to a whole number. It's 501. 3,000 times the complement is this. Second sample was 1,800 times the pooled, gives us this. And the complement gives us this. Same song, second verse. Again, I need to say, what am I comparing it to? Well, both are greater than or equal to 10, so the large counts test is satisfied. Okay, so moving on to the do step. Here's my formula. I take my 2 proportions, subtract them, minus 0, the null value. There's my standard error. Notice I use the pooled proportion in both of the fractions with the individual sample sizes. Crank out that number, I get 4.05 for my z-score. So I sketch my drawing. That's way over here as a right tail. It should be because it's a greater than. And I find that using my calculator, I get a p-value of approximately 0. Okay, meaning it probably was like some number times 10 to the negative 7, which is basically 0. So be aware of that. So it's approximately 0 p-value. Then I can draw my conclusion. Since the p-value is approximately 0, which is less than 0.05 or alpha, we reject the null hypothesis. We have convincing evidence that the proportion of all teens with hearing loss has increased from 1988 to 94 to 2005 to 2006. Okay? So part B of the question, between the 2 studies, Apple introduced the iPod. If the results of the test are statistically significant, meaning we reject the null, which we did, Can we blame iPods for the increased hearing loss in teenagers? Well, stop and think about it. Is iPods the only thing that could damage teenagers' hearing? Well, no. There's concerts, there's radios, there's all kinds of other things that could damage their hearing. So can we blame it on the iPod? No. Now, more specifically, it was not we don't have an experiment here, so we can't use causation. So we would say, no, we can't establish a cause and effect relationship without an experiment with randomly assigned treatments. And then I kind of defend it. It's possible that car stereos are too loud and causing hearing loss. You could say it's possible that concerts are too loud and causing hearing loss. All kinds of reasons that could attribute to hearing loss besides just the introduction of the iPod. Then, is it okay to use your calculator for the do step, and are there drawbacks? Absolutely use that calculator because it will save you so much time. All right? Now, you've got stat, you've got test, and it's test 6. It's 2 proportion z-test. Be careful that you don't use the 2 sample z-test that's in there. We won't use that one. We only use the 2 proportion z-test. Now, be careful because remember, again, it's going to ask you for x1 and x2, and those are integers. They are not percentages. So if you put in decimals, you're going to get an error. Just like I showed you on the confidence interval video, you've got to put in x1 and n1 as integers. And again, don't use the 2 sample z-test.